Hello everyone. Today let's solve some frequency domain analysis problem. First, let's look at the 2.1. Calculate the transfer function of the passive filter, showing the following figure and drawing the Bordeaux plot of the filter. Let's write the transfer function gs equal to ys divided by us, and here as we have learned from the lecture, it's equal to the odds divided by the e. That is this part is the odds, and this part is the in. And first, let's recall the impedance in the frequency domain, and the resistor in frequency domain is R, and the capacitor in frequency domain is equal to 1 divided by Cs, and also the inductor in function domain is Ls, and here we can write the Z-outs as this is a parallel connection, so this is equal to R2 cross product 1 divided by Cs. And this Z-in is like a combination of the series connection and the parallel connection. And first is the parallel connection, and is equal to R1 cross product the inductor, and plus R2 cross product the 1 divided by Cs. Okay, and then we can write for the cross product, we can write this equal to R2 times C1 divided by Cs, and divided by R2 plus 1 divided by Cs. Okay, and following is like okay, we write it R2 times 1 sorry, I missed S here. R1 plus yes. Okay, and then we can rewrite this equation, put here so first we multiply the Cs both in the denominator and the numerator, and it's equal to R2 plus R2 Cs plus 1. Here also equal to 2 plus R1 US okay, and then we substitute the parameters into the equations, and this R2 equal to 0.1 divided by 0.1 times 10 is 1, so it's as plus 1, also 0.1 is plus 1, R1 equal to 1, L equal to 1. Okay, and this is R1 plus EOS, R1E is 1 plus S. Okay, and we can write it both times multiplied by S plus 1, which is equal to 0.1, and S plus 0.1. Okay, and we multiply by 10, and it's equal to 10s plus 1. 1 divided by 10s plus 1. The reason we did that is we need to get a basic transfer function for the border diagram, and as we learned from the lecture, this transfer function is the one-time constant proportional style functions. So then we can join the border diagram. And so in case we get the transfer function of the filters, and we applying this as equal to I omega, so this G I omega equals 1 divided by 10 I omega plus 1. Okay, and this is a one-time constant proportional type, so we can join the border diagram. Okay, in case it's clear, I use right. And first, let's calculate the cutting frequency. And the cutting frequency is equal to 1 divided by t, which t is 10 here, so this is equal to 0.1. Okay, this is 0.1 cutting frequency. Okay, and and the slope is minus 20, as we learned from the lecture. Okay, and also we need to join the phase diagram. This one equal to 10 divided by t is equal to 1. This one is equal to 0.1 divided by t, which is 0.01. Okay, from here. As you can see, it's not the actual board diagram you draw from the MATLAB. It's just we apply this piecewise linear asymptotic approximation method, and for the exam, in this part you can join like by hand without the linear log paper. And then let's turn to another case. Okay, the second one, calculate the transfer function of the passive filter showing the figure. Draw the Bode diagram of the filters. Again, GS equal to YS divided by US equal to Z out divided by Z in. Z out only R2 here. And the Z in is the combination of the series connection and the parallel connection, which equal to R1 cross product 1 divided by CS plus R2. Okay, and we can write is equal to R2 divided by R1 dot product CS 1 plus 1 divided by CS plus R2. And we can write GS equal to R2 divided by R1 CS plus 1 plus R2, and which equals to let's multiply R1 CS plus 1, that is equal to R1 CS plus 1 1 Okay, that's to R1 R2 CS plus R2. R1 plus R1 R2 CS plus R2. Okay, and then we substitute the parameter, and be careful with the unit. We need to transfer the unit to a standard unit. So R1 is equal to 3000 ohm, R2 R1 7000, R2 3000, and times C is equal to plus R2 3000. Okay, R1 is equal to 7000 plus 3000 plus okay, and then it equals to okay, it's and it's 10,000. Okay, 10,000. And then we can write GI omega equal to 21 I omega plus 3000 divided by 21 I omega plus 10,000. And it's not a standard transfer function, so we need to get a basic transfer function to join the Bode diagram. And so first let's divide it by how much? By 10,000. Okay, here is 0.0021 okay, plus 0.3 and oh, sorry, missing I omega here. 0.0021 omega plus 1. So we need to get 1 here, so we divide it by 10,000, and then we what to do? And we put this 0.3 behind the function, which is equal to 0.3, and that one is equal to 0.007, right? 3, yes, I omega plus 1 divided by 0.0021 I omega plus 1, and yeah, we can put here times 0.007 I omega plus 1 times 0.001 I omega. Okay, what we did here is to make the denominator to become a constant, not included with this I omega, and we put this I omega in front of the function, and then we can get this transfer function, and we can know this is a 0 time constant proportional, and this is proportional, and this is 1 time constant proportional. So we got 3 basic transfer function here, and then we can draw the figure based on the function. First is the and if you remember, for the basic functions, the 0, 0, 0 TP is like it's equal to 20 times log 0.3, which is equal to minus 10.48458. Okay, which is 0 is minus 10. Oh, it's almost there. Okay, this is 20 times log 0.3, and it's so the whole figure begin with this one, and then we look at this PD, and it should be the omega the cutting frequency omega c is equal to 1 over t is equal to 1 over t is 0.007, which is is equal to 142.86, which is okay. We put here. So, and if the figure comes to here, it will have a plus 20 slope. Oh, okay, and we can draw it going up. Okay, this is the second terms, and the very last terms with 1 TP, and the cutting frequency again equals to 1 divided by t is 1 divided by 0.0021, which is equal to 476.19. Okay, and this 1 TP functions with minus 20 slopes, so plus 20 minus 20, and it's adaptive, so it becomes 0, and it becomes a straight line again. And this is the cutting frequency of the 1 TP system, which is equal to 476.19. Okay, that is the first diagram, and then the second one. Second one is the phase diagram. Zero here, and again, the 0 TP system is the straight line. Start with 0, right? Okay, we start with 0, and this is the second term. Sorry, the first term, and then we going to the second term, which is PD, and PD with the plus 45 slope, and the cutting frequency is 0.1 omega c, which is this omega c is for the PD system, and this equal to 14.286 is here. Okay, and this is omega c for this PD. This is omega c PD. Okay, it's going. With plus 45 slope. Okay, and that is the second term, and then we join the third term, which is 1 TP system with minus 45 slope. And again, it's going like this way, and until 0.1 times the cutting frequency of the 1 TP system, which is like 47.619 here, and this one's okay, and again the cutting frequency is 1 TP system, 476.19. 10 times with minus, this is with minus 45 slope, this is with plus 45 slope. Okay. And okay, we got this board diagram. And for the book, you can find the actual board diagram plot by MATLAB. Let's now look at reverse solution. So calculate the resistance R2 and the inductance L of the circuit shown in the figure. If the filter's step response is known as V when t approaches the infinite, is equal to 2 divided by 3 volts. And also join the Border diagram of this filter. Let's now write this G as again equal to Y as divided by U as equal to Z out divided by Z in, and this D out only R2, and Z in, this is a series connection circuit, so it's equal to R1 plus EOS plus R2. Okay, and let's rewrite this function. GS equal to, let's divide it R1 plus R2 on both sides. R2 divided by 1 plus R2, and that's equal to R1 divided by R2, R1 plus R2 divided by R1 plus R2 plus L is R1 plus R2. That is equal to R2 R1 plus R2 divided by 1 plus R1. So why we do this method is because we want to get this basic transfer function, so we can calculate the parameters. And if you look at this transfer function again, it's like one time constant proportional type functions, because this one is A, this part, and this is like I omega, a constant plus 1. Okay, and then we need to apply the final volume theorem like we did at the first lecture. So we write that limited t when t approaches the infinite is equal to limit when s approaches 0, s times ys. Okay, so we can say from here that it's the step response functions. So the ys equal to gs multiply us, and us equal to 1 divided by s. So So we can write here is equal to limit s equal to 0. The s times gs times 1 divided by s is equal to 0 gs. Okay. And we can write here that the limit when s approaches 0, gs equal to R2 divided by L1 plus R2 divided by L divided by R1 plus R2s plus 1. Okay, it's equal to when s approaches 0, so 0, 1. So this will become R2 divided by R1 plus R2, and we know that this one equal to 2 divided by 3, and we also know the R1 equal to 1, so it means the R2 divided by R2 plus 1 equal to 2 divided by 3, that's this equals 3. R2 equal to plus 2. Okay, and we can okay, so R2 equals 2 here, so we can get R2 equal to 2 ohm. And then let's calculate the inductance. And we can write again the G is equal to, where is that? Okay, equal to 2 divided by R1 plus R2 is 3. L divided by R1 plus 3 plus 1. Okay, and we can know that the T is equal to 2, so we can write that L divided by 3 is equal to 2. Okay, then we get L equal to 6 Henry. Okay, and then we can write the transfer function of this filter is Gi omega equal to 2 divided by 3, that 2I omega plus 1. And again, this is a one-time constant proportional type functions, and then we can join the Bordeaux diagram. And so for this time, A, okay, right here, A equal to 2 divided by 3, so we can write that okay, and this one is equal to minus 3.522. And okay, and we can write from here's minus 10 minus 20, here is minus 3.522. Okay, and the cutting frequency omega c equal to 1 divided by t is equal to 0.5. 0.5. So it should be like okay, the slope is minus 20. And that's this one. Minus 23.522 something. Okay, and we then draw the phase diagram. Okay, 0.5, and this is 0.05. And for the phase diagram, no matter this A equal to what, it's always start from the 0, and the slope is minus 45. Okay, it's minus 45. Okay. That's all for today. If you have further info for the problem, you can contact me. Thank you.